What's up? We're back. Part two. All right. So where did we leave off? Hmm, Here we were watching this video. We're doing this. All right. So reversible in this sense, yes. Reversible means every dimension increasing move adds such split a change point. So K represents change points. This guarantees the targets of the correct distribution over both where the change points and how many there are. Okay. Map old parameters. Select the change point to remove the map to neighbors. Acceptance is the reciprocal form. Does time refer to like exposure time? Both up and down in K in a way that exactly balances, preventing bias towards too many or too few change points. Cool. Okay, so ultimately I want to, this will be like the first figure, and I want to kind of have like a one paragraph description of this. So here is the overview of the model. The REX method attempts to model as a mixture of share its kinetic parameters across to the data demand a change point. Predict each peptide by summing over its covered residues to fit the observed uptake with length weight or Laplace likelihood. The reverse jump to jointly infer the number of positions of change points. Okay, this actually makes sense to me. The model predicts each residue's uptake as a mixture of simple and stretched exponentials. Share its kinetic parameters across neighboring residues until the data demand a change point. We predict each peptide by summing uptake over its covered residues and fit the observed uptakes with length-aware Laplace likelihood. I think we're just going to say length awareness. To account for noise. Noise increases with larger peptides. They use reverse jump MC to jointly infer the number and positions of change points. So these are change points right here. So this would be reverse jump move. The segment kinetics and the noise scale. I don't know what's meant by noise scale. Summarize the posterior. So is this the posterior? To obtain residue level curves with uncertainty, change point maps, and overlap aware diagnostics. Okay. Okay. So how do they avoid overfitting? I think that's probably enough for the first figure. I don't need to go into too much detail. I don't know what a non-parametric model is. An RAX not overfitting comes from the stack of design choices that reduce freedom unless the data truly demand it. Fewer effective parameters. Residue first plus segmentation. Adjacent residues share one kind of kinetic parameters inside a segment. Parameters only change at inferred change points. Sharing massively cuts degrees of freedom versus giving every residue its own free curve. Physical kinetics. Each residue curve is monotone, saturating, non-negative. Okay, well, priors that penalize complexity, Bayesian shrinkage. Poisson prior on the number of change points k. More change points, lower prior probability. Oh. You only earn them if the likelihood gain is big, otherwise the posterior prefers simple segmentations. Hierarchical priors on kinetic parameters. Gamma and beta priors keep rates, stretch weights in the plausible ranges, and borrow strength across segments. Extreme is back towards the group. Likelihood that's robust and length aware. Laplace L1 errors are robust to outliers, less temptation to chase a few bad points. Hetero syndastic scaling of peptide length. Long peptides are allowed more variance and thus downweighted so they don't dominate or force spurious local changes. RJ-MCMC proposes birth/death of change points, acceptance balance, the fit improvement into the penalty for extra parameter. Prior Jacobian. Unnecessary splits are rejected. Proposal symmetry. Consistent small effects add up. Isolated contradictory blips cancel. Discouraging overinterpretation of noise. They train on one protease map and predict unseen peptides. Penalizing extra segments via priors. I'm kind of interested in how that works. Explain how some of the priors that penalize more change points. And then I think I'm going to give it the paper again. Where are we? All right, in the meantime, I'm going to download this. What is this? TPO 42. Download. I don't know why, but the new VMD version doesn't accept .nc files, which is kind of strange. Sorry, I'm putting some music on. We're putting on Underworld. Okay. So let's do the same for these. There we go. We want to change this though to unmodified. CPV dredge. What pump it in? Alright, so let's see what it says. Here's exactly how REX priors penalize adding change points, model complexity, and why that keeps the fit from fragmenting into too many segments. Prior on the number of change points. Puts a Poisson prior on the number of change points. So, in log terms, the penalty added is when you increase K. What is it's Poisson, right? Poisson prior. That's what I was talking about, lambda. Gamma distribution. Oh, God. So, in log terms, the penalty added when you increase K. Log PK plus 1 minus log PK equals log gamma . As K grows, log plus K1 outpaces. So each extra change point is increasingly disfavored unless the likelihood gain is big enough to overcome the Occam penalty. Using Stirling's approximation, the tail shrinks. This reminds me of max entropy reweighting intuition. Lambda is your prior expected number of change points. Smaller lambda, smoother fits, fewer segments. Larger lambda, you're more willing to split, but you pay the K penalty. Given K, locations are ordered uniforms on the residue axis. The prior density for a specific configuration, this shrinks by a factor, so every split also pays a location penalty. So overall uniformity is preserved, but in the exception. Oh god. I need numbers. This is insane. But like most things with math, the functions look crazy, but in reality it's saying a very simple thing most of the time. Priors on segment parameters. When each k plus 1, all residues share one parameter vector. Yeah, so that's the you also add a full new delta block. The prior density multiplies to the posterior. What is a posterior? And math. Is a type of conditional probability that results from updating the prior probability with information summarized by the likelihood via an application of Bayes' rules. From an epistemological perspective, the posterior probability contains everything there is to know about an uncertain proposition, given prior knowledge and mathematical model describing observations available at a particular time. Probability may serve as a prior. This is stats to the max right now. You add a change point. You also fill a new theta block. The prior density multiplies into the posterior. Unless the data generally need those new degrees of freedom, the prior mass concentrates around typical values, which suppress gratuitous jumps. The hierarchical hyperpriors borrow strength across segments. Softly pulling. There's no way I'm going to be able to, even if I did understand this, explaining this, I think it's just a fool's errand to the people that are going to be doing this. So I think I'm going to give myself a deadline of like 1 p.m. and then we're going to have to move on to the next figure. Because I can't do that. TLDR. RX penalizes extra change points in 3 layers. A Poisson prior makes large K a priori unlikely. How about you explain what you just did, but with numbers, with dummy numbers, and put it into words, into a less abstract scenario. Like HGX MS. Properly motivate this with 2 with so we can understand why we need any of these things in the first place. State what would happen if we didn't do these things and why it would be wrong. Alright, let's see if we can do that. Alright, I misspelled modified. That sucks. Alright, I kind of want to look at the simulation real fast. I think I need to open up a new thing. Just go over here. We just did this one, results, Parm 7, load, DCD. There she is, whoops. We can do graphics, representations, new cartoon. So it seems like the zinc is kind of chilling right there. His name, ADP. I'm going to show this as licorice. TPO, CYM, ZNB. So what we got? Yeah, it kind of looks like it's not moving much from here. Yeah, this is comfortable within the active site, you know, but nothing much more than that. So, download that. Okay, here's a concrete HDX-MS flavored walkthrough with small numbers. Tiny HDMX toy. Protein stretch, 1 to 12 residues. 3 overlapping peptides, length 6 each. 1 to 6, 4 to 9, 7 to 12. Residue level uptakes add to the peptide uptake. Standard HDMX convolution. Error model, simplified Laplace. Log likelihood increases when the sum of absolute residuals shrinks. That's the error model. So the log likelihood of what? What is the... Okay, so the probability of this deconvolution increases when a sum of absolute residuals shrinks with scale B 0.05, dropping absolute error by, okay, there's a +1 in log likelihood. Model A, one change point, 2 segments. Assume a single boundary at residue 6. It's a shared uptake. Residues 1 through 6, share uptake. P1 predicted, 6 residual 0. P2 spans both. What is P2? Oh, I see. Okay. Call this our current fit. Okay. Proposed model B. Add a new change point, 3 segments. Split the second segment. So now adjust the last chunk downward, 7 through 9. Predicted. Okay. 3 Occam penalties with numbers prior. This is making sense. So use K equal, expect approximately 1 change point. Going from K1 to K2, so the log penalty is that. So we subtract that from the log. Prior unchange point locations, uniform ordered. 2 and 11. I gotta shave. 2 through 11 are potential boundaries. R minus 1 is 11. Priors on segment. Adding a segment adds a fresh parameter block. Suppose the prior density at the proposed values is moderate. The product of priors for the new Interesting. Why we need each piece and what breaks without it. So perfect. Underdetermined. You can always shave residuals by carving more segments. Without it, the sampler keeps adding boundaries for tiny gains. Sawtooth residue profiles that don't generalize to held out digest time points. Does mine kind of look like a sawtooth? Kind of does. Kind of does. Let's look. I think on the collab we have something. Looks pretty sawtoothy to me. But also, I think like it would be kind of salt. But it might just be that way, you know. Depends on where you're coming from. Like if I'm coming from the structure, it might be like that. I mean, mine does generalize to held out. I don't know about. I guess to yeah. So that location prior tau. Don't override arbitrary microboundaries. Why? Many possible cut sites. Picking a very specific split should cost some pendency mass. Without it, the algorithm is different, spreading boundaries everywhere. Local noise spikes become features. Shrinking hyperparameters. Guard against extreme tiny segment parameters. Why? Very short segments are poor or data poor. Unconstrained rates can drift without examples of kinetics. Orthogonal important linked where long peptides average many residues and are legitimately more variable. Downweighting their residuals prevents them from dominating the fit. Without it, the model would overfit the long peptides at the expense of shorter, more local evidence. Proposal must earn its keep. The drop in absolute residuals log likelihood gain has to extend a complexity total that combines the Poisson cost, more boundaries, the cost of picking a specific boundary location, and 3, the shrinkage cost. Don't. Alright, I think we need to go through this one more time. This is good though. Protein stretch, residues 1 through 12, 3 overlapping peptides, 1 time point. Boom, boom, boom. Okay, residue level uptake, add to the peptide level uptake. Error model, simplify Laplace. Log likelihood increases when the sum of absolute residuals shrink. What is log likelihood? Explains how well a statistical model fits the data. We have a diff. So the log likelihood is just a number that represents the fit of the data. Homie. Increases when the sum of absolute residuals shrinks. Yeah, with the scale +1 in the log likelihood. So you can define like a arbitrary thing. Model A, 1 change point, 2 segments. Assume a single boundary at residue 6. Total absolute error, this is our current fit. Add a new change point, 3 segments. Split the second segment now. So now 1 through 6, 7 through 9, 10 through 12. So we're splitting in between the splits. Oh, we're just splitting the second one. Okay. And adjust the last chunk downward. Predicted P3. Seven through 9, 10 through 12, 1 to 80. Now the total absolute error is 0.4. Error improvement 0.18. Delta log likelihood. Okay. So this clearly helps the fit. Do we keep it? So when we split, so at each split, are we changing the predictions? Prior on the number of change points. Use k Poisson lambda with lambda expect approximately 1 change point, going from k equals 1 to k equals 2. I don't get that function. I guess that's like something to do with like the probability of a two change points. So here are we defining lambda or gamma? Is that gamma? No, it's lambda. Lambda to be the expected number of change points. This is a hyperparameter. So when we apply the change or change points, this defines the likelihood likelihood this is realistic, the greater lambda, the more realistic, more change points are, and thus less of a penalty. Prior unchanged point locations, uniform ordered. Residues 2 through 11 are potential boundaries. R minus 1 equals 11. Oh no, R minus 1. For K, 1/11th. For K equaling 2. Huh. Two over 11 squared. Nice. We're getting somewhere. Alright, the prior on the number of change points K. So lambda is the prior expected number of change points. That's a hyperparameter. You can fix it, tune it, or give its own hyper prior so the model learns at 3 precise points. It doesn't change the likelihood. It only changes the prior odds of models with different numbers of change points. The posterior then balances likelihood fit versus these prior odds. Uniform locations. Yeah, I don't get the locations part. Tiny numeric field. Suppose the protein stretch, 60 residues, 59 possible boundaries. A prior factor per added boundary. Log penalty is that. Interesting. Okay. All right, I get that. We're at 1238. Okay. Prior unchanged point locations, uniform ordered. R minus 1 equals 11. I do not get how this encodes a penalty on positions. What is the residue index considered here? in the range. What is tau? Did I download this? Yep. Let's see there. File, new molecule, browse, here, results. Did I just download these? Oh, it's unmodified. Yeah. Graphics, new cartoon, great rep, res name, AMP. This would be ATP actually. CYM, ZNB, do licorice. Why do I select the first one? I knew that would happen. Is it ATP caps? No lowercase. ATP, CYM, ZNB. Okay, so yeah, same deal with this one. I want to look at THR as well. I wonder if this could be a second ATP site right there. That'd be crazy. I know what I need to run next. Like, how do you know if ATP can bind someplace? Yeah. All right. Let me pin down the symbols and what they. Okay. Tau is the ordered vector of change point locations along the sequence. The ordered vector of change point locations along the sequence. Tau 1 through tau k, with 1 less than tau 1 and tau 1 being greater than all the way to r. Okay. So these are basically indexes. So each tau j is a boundary between residues. If your protein has R exchangeable residues indexed 1 through R, there are R-1 possible boundaries between 1, 2, 2, 3. So the allowable positions tau live on a set of R-1 boundaries. If you label boundaries by the right hand residue index there, 2 through R, if the left hand, same thing. How does the prior encode a penalty on positions? 2 parts on the prior matter. prior on the number of change points k is Poisson. Oh, so there's a, wait, right. Such the complexity larger, right? Prior on the locations given k, uniform ordered over most of our boundaries. In the continuous ordered formulation, this is places each k points. No site is privileged. So k factorial minus r to the k number of possible sites, possibilities. Now look at the prior odds for adding one change at a specific boundary. Combine the two pieces. Poisson on k. So this is probability. Does the k is the number of change points. Cross multiply. The constant prior factor I get that. So each boundary pays the position penalty and tuition numbers. There we go. Okay. Say r is 50, r minus 1 is 49. If lambda equals 1, the prior factor 1 over 49. Where's that here? This equals 0.0204. Okay. 5. The proposed split must improve the log likelihood by more than this penalty. So, split easier. Does the prior favor some residues over others? No. With the uniform, all boundaries are equal exactly. Okay, I don't fully understand this, but that's okay. Why is it called Occam penalty? Maybe because it's trying to find the simplest explanation. Adding a segment adds a fresh parameter block. Adding a segment adds a fresh parameter block. Suppose the prior density at the proposed values is moderate, e.g. the product of priors for the two new sub-segments is about 0.25, while the prior density of the single old segment was 0.5. Acceptance score. What if improvement is tiny? Okay, we're at 1250. I think we can create a I mean, this is pretty cool, honestly. Like, this is like a way to basically find the simplest solution to a problem for HD, like HDMX, HDXMS. I still don't get this completely though. So at each change point, we compute new rates for each residue in that range, or do we keep? So when we or do, I mean, I guess we have to, right? Do we just predict ones that fit the data the best? Creating two new parameter blocks, left and right. These blocks then get proposed and accepted. It's not just about picking the best fit in MLE, it's about balancing fit and complexity through priors over iterations. Short answer, not one new rate per residue, it's one new parameter block per segment. And residues inside the segment share those parameters. And no, we don't just pick the single set that fits best. We sample from full posterior, so added change points must improve fit enough to beat the prior penalties. Here's a picture. Just correct. kinetic parameters as piecewise constant along the sequence. If residue, they all inherit the same block, only at change point the parameters jump to different block. So we aren't estimating a completely free set per residue, we estimate per segment blocks. What happens when you change the point it proposes I split one segment into two. Pick a boundary, propose two new parameter blocks, compute the posterior change, likelihood times priors, accept the split of the probability that increases only if the fit. So this is like a great summary, I think, right here. Where do the penalties come from? I know that. I mean, I don't get how jump to a different block. So what do you mean by this? Is it how do we compute the parameters for the different block? If we are subdividing residues, the peptide, where the residues in it all have the same rate of uptake, and we are how are the blocks different? If one division still has the same rate. So we place change points along residue. Yeah, between two consecutive time point change points. I get that. Peptides are observed. Alright, did we download this one? No. I think it's making sense to me. And I did it within an hour. Reading it out loud really helps. How are blocks parameters computed? They're not solved in one shot. They're learned by Bayesian sampling. For any fixed segmentation, a set of change points. Every residue in the segment K shares one kinetic block. Just uses Metropolis hasting updates. Propose a small perturbation and accept if it improves the posterior. Because the peptide model is nonlinear, there is no closed form. The sampler just keeps nudging towards values that best explain the data it influences. A handy way to see the likelihood for peptide, where WK is how many exchange the peptide ISO. Each peptide is a length-weighted mixture of segment curves. We jiggle sigma. Only peptides within greater than 0 change their predicted uptake. The MH step accepts a jiggle. Okay. The RG MCMC split picks a boundary inside a segment and temporarily creates two blocks, left, right, parameters. So it picks two, then it jiggles them. That adds a new column to the weight matrix. Peptides that straddle the boundary now get 2 weights instead of 1. 2 outcomes. Data support different kinetics across boundaries. When a sampler can set straddling peptides, and those that sit modestly on one side now fit much better, boosting the likelihood. Yeah. Okay. I see. So the difference between blocks is just nudging the subsection length to have higher or lower uptake. This is done randomly. I probably just worded it wrong, but I think I get the idea. Proposals are random, results are not. hour, so let's create the slide now. Insert new slide. So we want something that goes over like overfitting. Go to the bathroom with this. You guys can watch the movie. Let's go. While I'm gone. All right. Let's look at the ZDB first. From there. I think this one kind of goes off the deep end, if I remember. Yeah, so this is binding to an ASP residue, I think. Right, yeah. So we could test this idea out further. So yeah, I think it's supposed to stay there because these come out of the active site, pretty much. And I do want to try and see if an ATP will bind there. So we could run that simulation later, but all right, so we want to do what does he call it? Occam. Occam's razor for residue level uptake. So I think the assumption is residues. Residues near each other will have similar rates of exchange. Okay. Change points define where are places in the sequence where uptake differ from their neighbors. So penalties for adding change points. So the number more change points increase or decrease log likelihood. And from 1 to 2, the log penalty is that. Prior on change point locations. The goal is to maximize the log likelihood of subdivisions. Change points and uptake rates of those subsections. So we have a prior. So yeah, more change points decrease log likelihood. I still don't get that necessarily. Tau is the ordered vector of change points along a sequence. Tau is bounded between residues. If your protein has index 1 through R, those are possibilities. Two parts on the prior matter. Prior on the number. Yep. Prior on the locations given K. Uniform ordered over. I don't know what that means by uniform. Okay, so they're subdivided maybe evenly. It's an Occam factor because prior mass is spread over many possible places. Oh. I still don't really get the point of that. What is R here? Can you? I get how the number of change points is penalized, but not the positions. Are subdivisions always spaced evenly? Or is it a random subdivision attempt? Okay, there's no direct penalty on position, so that's a wrong way of putting it. Okay, only on how many there are. Given a fixed number k, all placements are the prior equally likely. Subdivisions are not forced to be evenly spaced versus random split locations uniformly and accepts them only if the posterior, yeah. So the prior actually says about positions. And split position uniformly random. Move split. Shifting tau locally. What is tau again? Tau is the boundary between residues. Okay, finish this slide, please, given the conversation we have had thus far. Match the tone of voice, please, and provide a brief explanation. I wonder how it decides to give response 1 and 2. Memory resonance tend to have similar exchange kinetics, change points, positions, and sequence, where those kinetics jump. Goal: maximize the log posterior, not just likelihood. Fit, size penalty, position, prior, regularization. Penalties for adding change points: Occam, complexity, penalty, via prior, and K. As K grows, dominates, extra splits are downweighted unless they greatly improve fit, prevent spiky overfit profiles. To evidence, marginal likelihood penalty for weak/short splits. Even with the proposed slit, if overlapping peptides at the time course don't show a real left versus right difference, the likelihood gain is tiny, so the posterior rejects it. Very short segments are naturally disfavored. Notes and positions. Giving K kind of like that. All right. Penalties for adding change points. Model size penalty. With K, so extra splits must pay for themselves, prevent spiky. Occam's less marginal likelihood penalty. Each new split creates a new segment with its own kinetics. Unless the overlapping peptides flanking the split truly behave differently, the improvement in log likelihood is tiny and the posterior rejects the split. Very short, weakly split segments are especially disfavored. I like this one. I mean, this one's nice because it gives that function. I like this one. So I probably should put in the, do they provide that in the paper? Where are we? That. I'm gonna drop this in here. Just do this. Do 14. There we go. All right. So let me see if this makes sense. Neighbor residue set up similar exchange kinetics, change points, positions in the sequence where per residue uptake model jumps to a new parameter set. What? Maybe drop the objective. Fit change point locations and segment kinetics by maximizing the log posterior log likelihood plus log plier, i.e. only add complexity when the data earn it. Penalties for adding change points. Model size penalty on count. A Poisson prior on the number of change points. The log terms fast with k, so extra splits must pay for themselves. Occam's/marginal likelihood penalty on usefulness. Each new split creates a new segment with its own kinetics. Unless the overlapping peptides flanking by the split truly behave differently, the improvement in log likelihood is tiny and the posterior rejects the split. Very short weakly supported segments are especially disfavored. Where can I edit this? Write this again, but no functions, please. delete this. Okay, definitions, assumption. Nearby residues tend to have similar exchange kinetics, change points, positions in sequence where per residue uptake model jumps to new parameter set. See equation. So that's the new parameter set down there. Objective, fit change point locations and segment kinetics by maximizing the log posterior. So log likelihood plus log prior, i.e. only at complexity in the data earn it. Penalties for adding change points. Model size penalty. Every extra split makes the model more complex. We use a prior that prevents fewer splits, that prefers fewer splits. So new ones are only kept if they clearly improve the fit. This prevents overfitting and overly jagged residue profiles. Usefulness penalty. Even if you try split, it won't stick unless peptides crossing that position truly behave differently. Tiny or weakly supported segments don't buy enough improvement, so they get pruned. I think that's a good, like, easy, sort of digestible summary. Obviously, we're oversimplifying like crazy, but now we can start attacking like the accuracy. So that's good for now. All right. So let's do benchmarking. So I think now we could probably start a new conversation. So I think I'll start from the top up here. There's like a lot of compacting that seems to occur. Display, background. Why is the, like at least have like white as like an option, you know? I think in the new version of whatchamacallit, VMD, they do that. There's some interesting secondary structures that emerge. Maybe not. And one of them there was, I remember. Like, here, I'll load it. Why can't I see it? There we go. Maybe not. Oh yeah, there is right there. That's weird. Why does this have so many more frames? Why does that happen? Okay. I know what I have to change, I think. REX frames residue level inference as Bayesian change point problem on the parameters of a monotone kinetic model. Peptide signals are linked to residues by summation. Laplace error inference uses to infer both number/locations of change points and segment-wise kinetics. The parameter benchmarks in cytochrome C, triple digest, leave digest out, reports fewer physical violations than alternatives, introduces, that is I think that's a dumb benchmark, but reduces sigma per residue. It could be dumb. It could be actually a fine benchmark, but I just don't understand it yet. I want to be respectable. I need to eat lunch. Digest, that's triplicates. Hold on. Alright, I want to do something fun. Compare it to this paper here. What results seem more promising? With complete non-bias. Let's see. I'm actually going to blank my screen out real fast. All right. Let's see what bot thinks of my attempt versus theirs. Let's see if there's any other new stuff, bio or for residue level. Calculating highly localized protein stabilities. What was this? October 23rd, literally yesterday. Where were we at? Columbia. Is it just the abstract? Protein stabilities. PFNet instantly determines 4 arbitrary large protein complex from conventional level, peptide level, and unlocks full potential of HX, such as most democratizing method and establishing quantitative scalable. Okay, let's see what we got. Uses a CNN encoder decoder. I like these pictures here. They model back exchange. They deposit their T4 lysozyme. First thing I want to see is an actual versus predicted, you know. But I guess they're measuring something different here. Start it. Um, hmm, I don't see anything. Okay. If you already have HDX and want residue level with calibrated uncertainty and error control, more mature choice is built from bottom up respects physics. Want to predict. Generalize. It shows strong leaving out. Works with from alpha and can be paired to reconcile rather than competing. We already know what that does. Mm. Oh. Okay. That's fair though. All right, so elaborate on the leave digest out benchmark. What is the rationale behind this? And what did they do exactly? Let's look at, where did that go? Where did that paper go? China. Okay. Kyle C. Webner. Wow. That's a lot of citations right there. That's cool. Nature, chemistry, biology. So this is already in nature then. This one's using Bayesian Monte Carlo, which I just learned about. All right, let's go back and see what else is there. Context. I don't see really anything else. It's definitely a paper to look into, though. All right. Each makes bottom-up data depend on protease used. Different protease cut the protein into different overlapping peptides. If a residue level method really works, it shouldn't just fit one peptide tiling. It should capture the underlying residue kinetics well enough that, trained on one digest, it can predict the uptake for different digest. Same chemistry, different cuts. Okay. What they did, protocol. Cytochrome C, different time points. 3 separate protease digestions. Fully deuterated controls. Alright, we're at 2 hours. Alright, I think I'm gonna take a break here. Eat some food. I probably won't be back today, so peace out.